seriously misaligned that. Perfection. Okay, nice. Welcome everyone to this Turku Meetup, CNCF Cloud Native and Kubernetes Meetup. We're really happy to be here at Sitowise today and discuss some recent things. With me, there's the other organizers as well, Sami, Erik, Anton, and we should actually put in the clicker as well to make it work. Yes. So is there anyone that's the first time here today for a meetup? Okay, awesome. Welcome. I'm really glad to see that. So a little bit introduction to the community first, and then we'll go over to Sitowise presentation. So we're part of this kind of bigger umbrella, the CNCF, which is a Cloud Native Computing Foundation, but also this kind of more local Nordics community. So if you go to cloudnativenordics.com, you will find a Slack that's open to anyone to kind of discuss with your Nordic colleagues. Also, we have 2 other meetups in Finland that we're running, Helsinki and Tampere, and the Helsinki one has the next meetup in 28th of February, and Tampere it's going to be announced, like maybe it already is, or like in an hour or so, 5th of March. And all of these meetups are streamed, so we have the live stream on YouTube on the Cloud Native Nordics channel, so you can follow them from wherever you are, which is the idea. So yeah, welcome all new members. We have now 184 here in Turku and nationwide 1,720. We follow the CNCF code of conduct, so essentially be respectful, include everybody, be nice to each other. So yes, cloudnativenordics.com for the Slack channel, then YouTube, you'll find all of these recordings. We're always looking for speakers, so you can contact me if you would be willing to discuss something in this future meetup. It's really just anything that you are kind of doing or kind of what you would like to discuss, or maybe you want to, I kind of fancy the thing where if I want to learn something new, I kind of sign up for a presentation about it, and then we'll see how it goes. So what is CNCF? It's essentially an umbrella foundation to bring all of these cloud native things together, all of the open source projects. It consists of end users, organizations that are vendors, and then also some technical experts to include the projects. There are essentially 3 levels of maturity of the projects. The first one being, or the kind of lowest tier being the sandbox, to which almost any kind of reasonable open source project can apply to become part of the foundation. And the good thing about doing that is that then a lot of kind of different organizations can collaborate on the project without being kind of worried about immaterial property conflicts. So even if it's an open source project, if it's only one company that kind of has all of the immaterial property to it, then other companies may not want to contribute. But if it's in CNCF, which is a non-profit foundation under the Linux Foundation, then anybody donate it there, and then anybody can kind of contribute. And then CNCF also helps with a lot of other things, like with project support and documentation and events and so forth. Then incubating tier is kind of, Fire already has a lot of production users and is proven to be stable and all of these kind of things. And then once it's kind of crossed the chasm and everybody's using it, then it can become a graduated project. So here are a couple of the graduated projects. Kubernetes being probably the most famous, but there's a lot of other good things in here. Containerd, for example, is the lower part of Docker. Then etcd is the storage of Kubernetes. Prometheus is monitoring the update framework you're using every time you pull a container. Fluent delogging, Helm, probably a couple of you have used for kind of Kubernetes package management, and so on and so on. Even more incubating projects, you know, and then even more sandbox projects. So there's a lot of things to digest in here for sure. And you know, if you have anything about any of these projects that you would like to kind of discuss or hear more about, then let me know and we'll figure it out. So what does CNCF do? They make a landscape to kind of help you keep track of all of these things. End user tech radars, like what are people actually using in production. Then kind of where are the companies at the moment. Then they do certifications. So if you want to learn about Kubernetes, for example, then there's a massive online open course MOOC on EDX. There are a lot of exams or certifications you can do. The lowest tier being the associate exam, then you can do the application developer, then administrator, and then security specialist. But also there's a lot of other things that are not connected to Kubernetes. Then if you're a vendor that is kind of providing services, then you can become a service provider. If you make kind of distribution on top, you can be certified from Kubernetes and so on and so forth. But there's also a lot of other things. There's an ambassador program, which kind of helps coordinate these meetups. So, for example, I'm an ambassador, so kind of just voluntary role, like help make things happen in your country. Then there are a lot of mentorships. There are Kubernetes community days. There was one in Denmark last fall, and now one in Norway a couple of weeks ago, and lots of other places as well. So kind of these smaller conferences, kind of 1-2 day things. And then there's a big KubeCon Cloud Native Con, which is now in March. I will share a discount code in a minute when I get off the stage, and so you can, if you haven't already booked, then get a little bit more incentive still to go. In the past, there's been, I would guess that it's 10,000, maybe even a bit more, possibly, attendees to this conference, and it's really a lot of fun, very educational. I always learn a lot when going, and yeah, essentially. That could be a good thing. And then if you can't make it to this one, then there's one always in Europe in the spring, and then in the fall there's one in North America. So Salt Lake City is coming in, was it November or October or something. So yeah, that's the intro. Welcome to this community. Is there any questions, or should we proceed to Tuomas' talk? Perfect. Let's do it. Take it away.
Yeah. So, great to have you here. And I have to spoil it in the first that I'm not going to discuss any about Kubernetes. questions as always.
This is going up there.
Okay, very good. Yeah, so I will not talk about Kubernetes. I will talk about.
I'm sorry.
Yeah, I shouldn't talk about.
Yeah, if it doesn't work, then we'll just go for the.
Okay.
Well, it's these kind of homegrown solutions, you know.
No, it's not working.
Should we just film the screen and then?
Yeah, I can do that as well.
Yeah. So like skip the screen.
It's the classic, like it worked when we tried it before.
It worked on my machine.
It worked on my machine. Joo.
Yeah, I will not speak about Kubernetes. I'm here to learn about things about Kubernetes, and I must be honest that there was a few days in work that I got to study about Kubernetes, and the documentation was that awful that I think I would never accomplish this. So that's the reason I'm here. And we talk about this kind of subject that what I'm working on right now. Really legacy software we are creating in cloud environment in Azure specifically, and there might be a need for Kubernetes I think in cost-wise also, so that's the reason why we are interested about the Kubernetes. So a few words about the company. Anu forced me to do this. Yeah, no, he's there. But basically, Sitowise is a big group. We have a building and architect stuff also, but we have the digi section also here. So we are basically doing software, different kind of software, lots of customer-oriented software development, and you will see the customers lately, and that's our customers is the reason that we don't have that much of cloud-native stuff, and you will see it lately. And then there is also some software products that I'm talking today, and then there is lots of specialist services and consulting. And basically, Sitowise is I'm missing one slide, but we are basically doing spatial software development. So basically all our applications have some kind of map or some kind of spatial data behind it, and that's I would say that 95% of our projects are some kind of related to the spatial data. And there is things that we are doing, lots of different languages and stuff. Have been many companies we have bought, little ones, and of course when you buy a company there comes different kind of legacy systems, and that's the reason that we are having these kind of technologies right now. Yeah, and here are the customers, lots of public contractors that we are doing, and some smaller companies also. That was the company thing. And yeah, Louhi is the one of our Sitowise digi products, and I can see here that, for example, Helsingi's map service is running on Louhi SaaS, but now all the Louhi applications are on-premise. They are in customers' own servers and stuff like that. And the biggest reason why we are moving this to Azure, we have let's say we have like 15 customers, and one software update could be like 1 day or 20 days or maybe more. And there is no proper CD pipelines and stuff like that. So this is the end of the road for the on-prem stuff. Yeah, it's a KISS platform. There's lots of spatial data, basically map. Then there's lots of microservices for different kind of things. I have not been developing the Louhi. Louhi has written with the .NET and jQuery and Angular and so on. I'm basically more on a Java guy and React guy, but because of the Azure, I got involved in it, and I have been with it like 6 months now doing the Azure stuff. So if you have application-specific questions, please ask. I'm not sure if I can answer them. But yeah, the basic thing was this, that there's almost 20 years of legacy code, different versions, different frameworks, without any unit or integration tests, and we should move this to cloud. So pretty easy. Why Azure? I think that there was some decision made before I got on board that Azure is the thing that we want to make it, and there is 20 customers hopefully in future, and now I think they're 14, and they have on-premise without proper CI/CD. And as I said, that version updates can take like 1 month, so it's not good place to be. The trickiest part was that I'm not familiar with the .NET versions that much, but the developer said that if we want to Dockerize the microservices, we need to make the version changes for the .NET that they can be Dockerized, and so there was pretty much of a refactoring, and then the code and the whole. There is lots of databases. Exactly, there is MS SQL, there is Oracle, there is PostgreSQL, which different customers are using. So all of these databases has to be in multi-tenant mode also, and the big picture is that let there only be one instance of everything and not customer-specific resources. So that's the Azure goal. Light in tunnel. We have a working Azure environment right now with the proper CI/CD for application and Azure infra, and it's in pre-production mode, and we have one customer that will be testing it in 2 months, I would say so. So big things coming. The next iterations is concentrating lots of testing on how to make proper unit and integration tests, both for application and for infra also. So we are using infrastructure as a code. We are using Bicep, and there is these Azure tools, ARM, TTKey, validation, and PS rule, which you can write unit tests for IAC templates. This will be part of for our infra CD pipeline. So then there is this whole picture. I'm not sure how small it is. It is really small, but no virtual machines at all. We are using for now we are using app services as a for microservices. And for now there is like this, there is 2 different microservices, but Louhi has like 15 microservices, but we are refactoring them like one by one for now. And this is the place that I think that we are maybe going to need a Kubernetes, because for now in Azure, when you're running app services, it's not that cost efficient. They are pretty costly, and also there is lots of boilerplate. We have lots of same kind of IAC code because of these app services doing basically the same thing. Big picture with the CD pipeline for now is that there has been a legacy thing called TeamCity, which builds and deploys the application. And now we are still running the TeamCity, but we are in future moving to GitLab because of security tools and stuff like that. But for now, TeamCity is building images in Azure Container Registry. And then we have Azure DevOps, that where are the IAC templates and the pipelines for now. And something else interesting about here. Yeah, our Azure secure points are like 84 up from 100, so we are pretty decent with that. And we have a security engineer who has hardened this SDG environment, so we are pretty good with that.
Question.
Yeah.
How many people do you have working on this, getting it to work in the Azure?
Oh yeah, good question. So there is 6 persons in developing team which are doing the microservices and the Docker containerization, and basically there was 2 guys that has done all the Azure stuff, and I'm another one of them. So the Azure is pretty much by 2 guys. And we have we can show if Bicep is not familiar to you. You're seeing my, yeah. So there is all the Bicep code that we are creating. There is this main templates.
You need to zoom in quite a lot.
Oh, okay. Is it Command Plus?
Should be.
Any better?
Yeah.
But yeah, I'm not sure if you are familiar for the Bicep language, but it's pretty decent, I would say so. So here are all the resources. For example, we have different app services here. We have here application gateway, different network security rules, and app configuration store. We have Redis, different databases, MS SQL, and PostgreSQL, Service Bus, and stuff like that. And this is running in Azure DevOps as pipelines. Yeah, I think this was it. It was my last slide. Please ask questions. Yeah.
To get a better understanding of what kind of microservices you are migrating or like updating and so on.
Yeah.
What this Lohi application, I'm not familiar with it.
Yeah.
What problem does it solve, and can you give an example of what kind of microservices you could see there?
Yeah, good question. Let's say lots of municipalities use this Lohi. For example, that there is a street light which is broken, so they want to give a feedback for the Turku example that this street light is broken and we need to fix it. So basically, the feedback service is a microservice where is a REST API, and there is this own UI also, which is integrated into Lohi. So this is one of kind of microservices, and same kind of microservices. There is lots of, like there is this some simple form, and then there is a backend for it. So microservices are pretty simple in that way.
Another question.
Yeah.
Is like most of what is it really that's difficult about making these containerizable? Is it like making sure the environment works correctly, or is it just updating the versions? Or
yeah, if I understood correctly, when you are updating the set of the .NET versions, you have to refactor pretty much the code. If there is this, I heard that the developers were talking about the cache stuff and stuff like that. So you have to like refactor it whole thing, and it was like 10 or maybe 15 years old code. So.
And was there like that a lot of these versions that have been deployed like on-prem for each of the customers? They each have their own different versions.
Yeah, that's true also. Yeah.
So you just like unifying it, so it's all just one code base instead of 20 different ones.
Yeah. So there might be like 6 different versions from the same microservices and stuff like that. So it was pretty hard. Yeah.
How long have you been working on this, like this entire migration thing, but also like this architecture? Like how much time are we talking?
This Azure architecture is like 1 year of like some kind of doing, like hard working, 6 months.
40 people?
Yep. Yeah. And basically I wasn't that familiar with the Azure. I started almost from the scratch. There is one Azure environment that I have done before this.
So you said that there wasn't really that much unit test coverage and stuff like that. So
yeah.
was your approach to first update test, or did you just YOLO it?
It's YOLO it because there is this kind of really stupid customer contractors, and we are already late, like 10 months, and so basically the thing is that we need to have something to see for the customer, and after that we can approach the thing and do the testing afterwards, which is not great, but
so
this is business.
If it's 10 months late and it's been under work for like a year, did they expect it to be done in 2 months then?
No, I'm not sure if there was any time scheduled for this, and I don't know the whole history behind this. But yeah, there was lots of problems in the beginning when this project started. When they decided to go to the cloud.
Is there anything that you would do somehow otherwise if you were given the opportunity to do it all over again?
I'm pretty pleased about the Azure thing here, but the application refactoring, yeah, there might be some things. I think that's the biggest reason why we are such a late now. And of course, when it's a huge applications that much of years, I would start it so that I would run a virtual machine in Azure and put ease there and run it like it's running in on-prem, and then I would like go in smaller pieces and refactor them. But now they decided refactor the whole core at the once, and it's always it's really hard to say is it a month or a year. That's one thing I would have done otherwise.
Do you think there is any service that you won't be able to migrate into Azure?
No, I don't think so. Because the microservices are so simple, and basically they are like exactly the same, but in different substance. So I think this is possible. But yeah, there is lots of performance testing, because when there's 14 customers, it's totally different than when it's one customer. And there might be on Helsinki map users, I would say, easily 5,000 in 1 hour or something like that. So still lots of to do.
Does it scale automatically, or is it?
Yeah, it doesn't scale for now, but all the app services are like, yeah, there is 2 instances for each app service that we have, so they scale that, and then we can scale it automatically because Azure App Services have that kind of attributes there. So basically we can do that, but we have to test it that how it really works. So we haven't done that yet, but it should be definitely possible.
Is there anything that will be changing from being like a microservice or whatever to being turned into something like a Lambda? I don't know what the terminology is because I have never used this. But
yeah, they are Azure functions in Azure. Yeah, we have talked them, and definitely it might be future thing that we would call them. Also,
Azure also have their own container platform, so you wouldn't need to use Kubernetes if you don't like to.
Yeah, that's true. But I have well, there's different opinions also. But the Azure Kubernetes cluster, I have heard that it's better than the Azure own containerizing system. But
it depends on what requirements you have.
Yeah, that's totally true. Yeah.
Since you come from on-premise and now have refactored a lot, have you added like tracing and stuff that you usually don't see in on-premise environments? Have you taken the time to like add the extra insights like telemetry stuff?
Yeah. Good question. We have here logging and monitoring. So basically all our resources are writing their logs in the log analytics, and also the app services are writing the log analytics, and then we can check the app service stuff from application insights, and also monitor about the resources. And yeah, it's definitely a huge thing for us, because now we can, like, when you are in on-prem, there is also might be some third-party CKE or whatsoever, and when you want to see the application gateway logs, you never will find them and stuff like that. Now we can see everything. And exactly, I asked our IT that we could have a Azure Copilot. It's in preview, and when I was watching the Azure Copilot thing, there is this that you can basically tell Copilot that I want this kind of dashboard with this kind of monitors and this kind of logs, and it creates you automatically, and it would be really good and amazing tool. Because the log analytics and the monitoring in Azure is not that simple for now, and there's also lots of things changing all the time.
Was this whole logging and stuff something that your customers wanted you to feature in this, or did you 2 people on the team just put it in?
It was our own decision to put it in for the application and for the resources. There is also customer things, basically for the GDPR logs, but they are in different place totally. But yeah, the monitoring, I think in nowadays, when you don't know the bandwidth and how many users there are, so you have to be pretty sure about all the steps that they are going through. Really good questions, thank you.
So is it automatically deployed through some CI/CD pipeline then from TeamCity?
Yeah, so basically when there is a pull request going there and there is some master branch updating, then it's straightly building and deploying it to the container registry. And yeah, there are webhooks that are checking that when new image is coming from the latest tags, then it's immediately in running.
So now you have the same application running for all the customers after this. So it's
Yeah, that's the big goal. Yeah. So we have a
How's the data then? Is there, is that multi-tenant also, or do they still have their own database?
Yeah, good question. There is a different things for different customers. There is these kind of customers that they have totally their own databases in their own servers, and then we are using a hybrid connection for now for reading the data from their servers. And then there is these customers that don't have that much of data. Then we are hosting that data in Azure, and yeah, there are many things for the databases and the data.
But you're not looking for one database for all the customers?
Yeah, no, because there is lots of these things that they really want to have their own data in their servers, because they have these spatial data updating systems, and it would be a total mess if we would stab it. So. Yeah.
So is it mostly, if you would use Kubernetes, it's mostly like for the scaling and kind of bin packing cost efficiency?
Yeah.
Reasons.
Yeah. Basically for that. I would say so that these microservices now are like basic, with basic license or SKU, how they say in Azure, but they are like in cost-wise. Should I say 50 or 100 euros a month, I think.
Mm.
Basically, if you have 15 of those, it's easily 2,000 euros each month. Just a rolling, simple microservices. So. But this was the app services were familiar to me. I knew that this is the thing that we can start with, and we see that the Dockers are running and stuff like that. So, but this is totally the thing that we have to check in future.
If many of the decisions you made was based on your experience from before, what kind of things have you done with Azure before this, or cloud computing in general?
Yeah, I have done 2 smaller Azure environments, which were lots of not that difficult. They was simplified. There was like one UI, one backend, one database, an application gateway, and virtual network, and that's about it. So lots of studying, lots of reading, and the other guy is also more familiar with Azure than I have, but I have written the bicep templates basically, but she's been helping me on my nights that I can sleep. So.
Do you see better performance in Azure?
I have to say that not yet. I think we have performance issues, but I think that they are coming from the refactoring and the hybrid connection that we are using also. It's kind of, I'm not that pleased with that, but customers say that we cannot do a side-to-side VPN in their production, so okay, this is one thing, but yeah, there is some performance issues that we are having right now, and there is of course there's lots of data in customers' environment, because there is multiple maps and stuff.
So if they are still enforcing that all of the data should be locally, I don't know, in their own data center or where they have the data already, why move parts of things to the cloud? Like, for them. Like
Yeah, so-
for some of the customers, they just want to have it hosted somewhere, but for
Yeah.
the customers that already don't want to move their data, where they kind of negatively, do they see it negatively that now the kind of core service is going to the cloud and then
No,
you need to call back?
no, I don't think so, because there are so many other things that we can like rapidly do the development and they can see the new stuff that is coming out, because the latency of the on-prem updating was so big. So the projects were like huge because of that. So
how many deploys are you doing basically per month or?
deploys in application-wise.
Yeah.
I would say that for now, for QA environment, it's like every day.
Yeah, that's nice.
Yeah. For application-wise, Bicep is now on hold a little bit because Azure is working, but yeah.
Which region are you running in? The Sweden?
No, West Europe.
West Europe?
Yeah, for now. I have this week I have done a disaster recovery plan and I'm running this in Sweden, but there is this PostgreSQL resource that it's saying in Sweden that Azure doesn't have capacity, so I cannot run this up in Sweden. But these kind of stupid problems there might come and then you are like kicking your head in a wall.
Do you know if they considered Google Cloud, which has a region?
No,
in Finland?
I don't think that they was thinking about it.
Azure is now building their own.
Yeah. Yeah.
Was it somewhere in Espoo?
Yeah. I haven't been that kind of Microsoft guy, but I'm really pleased about the Azure and the documentation and the examples and tutorials. They're really good. And you can like achieve a lot in short time.
So you don't have a strategy or plan that you could change the
No, yeah.
built for this?
Yeah, built for Azure.
Yeah. Change the cloud.
Yes. Is that something that
If you ask OpenShift guys, yes.
And there was a question about this, that we should write the IAC with Terraform, and then I decided that no, it's really not that simple that we just writing a Terraform, we can run this in AWS. It's not going to work any day for now. I'm thinking about that, but and that's the reason why we would choose the Bicep language.
That is at least one of the benefits of Kubernetes. That if you want to do all of the things in Kubernetes,
then you can run it like when you want it.
You can choose them.
Yeah.
But it's just nice to see you have lots of other bigger fish to fry now.
Yeah.
Before.
Yeah.
Yeah, thank you very much
Thank you.
for the presentation.
Is that the door or what?
Yeah.
What is it?
No idea who is who.
is the door still open?
Yeah, let's have a break. I don't know, 20 minutes. We have lots of time. great. Great that you had so much to talk about. We can continue in 25 minutes or so. I'm sorry to disturb. But yeah, let's get this done with, and then we can continue networking, and people will also have seen it on the stream. But yes, I'm gonna talk a little bit about databases in Kubernetes. Anton talked about this in the context of PostgreSQL operator last meetup, which was nice. Anton had a lot of good live demos. I don't, unfortunately, but I'm gonna rerun a presentation that I did in Mountain View in the fall. So a little bit different focus than during that, but still. So it's good that if you were at the last meetup, then you can then maybe you remember Anton's thing, and even if you weren't, that's the whole point of recording these meetups, that you can go back and check what he did. And for those that are the first time at this meetup, then you can also go back and see what Anton demoed, which was a really cool live demo. But I'm gonna be more on the talk more about the philosophy side of these operators. So why do we design software the way we do? A little bit about that. And yeah, I'm Lucas. I've run these meetups, been a Kubernetes contributor for a long time. Yeah, doing these kind of, if anyone has used kubeadm for installing a Kubernetes cluster, then I'm the one to blame. I'm sorry. Yeah, I study at Aalto University at the moment still. Yeah, a little bit about database complexities. I will have a screenshot from the demo that I did, and why we have operators. So let's go through that. So when we talked about data stores in the cloud and in different places, what is hard about data stores? There's lots of things, and yeah, actually, so this talk also stems from that I wanted to learn more about databases, so then I signed up to talk at the database conference, right? So now I've read a little bit about that. So Google has two really interesting papers that you could read if you're interested in these things as well, Spanner and Percolator. I think Spanner is the most amazing one, where essentially they have built a globally distributed database that is SQL-like, but more kind of on the key value side of things, where it's essentially externally consistent. So that means that if you, it will process all of the things exactly as things come in the right order. So that is a really, really hard thing to do globally. So like if you send something in Japan, I don't know, 18:00:01, and then you send something in the US in their local time, 18, or like similar time when you remove the time zones, 00:02 or something, then that one in Japan should go first, and then the one in US should go second. How do you coordinate this when the milliseconds, even just for light to travel around the globe, takes a fair amount of time in milliseconds? So they have solved this using some really clever machinery and atomic clocks and GPS things. So I highly recommend reading the paper and on how they did that. The most kind of telling quote was that they stated that actually atomic clocks are not that expensive or hard to use compared to the GPS ones. Yeah, but with those kind of, and then they have another version of kind of more for large data processing. Anyways, just a really, really kind of high level things. We want to have fault or failure tolerance, and also kind of the ability to meet capacity demand. So, well, when it scales, then we should be able to handle that, but also without losing any data, right? So that we need multiple replicas. We need multiple. We can't do any more with one machine. I mean, if you have one machine, that's complete optimal. Like, always go for one machine if you can do one machine. After that, just everything starts to, then you start need to think about, relativity theory of speed of light and that kind of stuff. If you have two, if you have one clock, you know exactly what time it is. If you have two clocks, you're not sure. And then if you have multiple replicas, then you need to have some way of kind of solving the conflicts. When one node says that I think this is the latest revision, and the other node thinks no, this is the latest revision. How do you solve it? So that's consistency control. Google uses Paxos, but there's also a kind of more simpler variant to implement called Raft, which is essentially used in all of the open source ecosystems. So Kubernetes, for example, uses as its backing storage a Raft implementation, which kind of the default or recommended is maybe 3 to 5 replicas or something like that of this etcd database, it's called. So that's why Kubernetes can be kind of highly consistent, because it has a highly consistent database in the backend. And then you need, once your kind of capacity grows even more, then you need to start shard your data as well. So there's a lot of things to unpack. And this is kind of just, scratching on the surface, but still. When we have multiple nodes, we need some scheduling logic. When we have these kind of Paxos Raft consensus algorithms, we need to take care when we're scaling. We need to, if you scale up, then you, kind of the baby, can't start receiving requests directly, because there needs quite a lot of time. If you have terabytes of data in the existing database, before you have transferred all of those terabytes of data to the kind of newborn server, it will take quite a lot of time. So you need to kind of take care when scaling up and down for these learner modes. And if you're upgrading or kind of doing some rolling upgrade, you need often there's a leader in these consensus protocols, and so don't kill the leader at least. Give it a little bit of time to do a proper handoff. Nodes have varying set of data. One node doesn't have all the data anymore, so now we need to kind of take care when we're sending requests, like where should we send the request. So yeah, lots of different changing requirements from customers, all of these kind of stuff. These are just some of the reasons of like why this problem is hard. So this is a kind of setting the justification for these kind of things, right? More high level. Every non-trivial thing requires non-trivial operations, right? Very simple statement, but at least it feels like. I mean, this is mostly empiric, but the amount of work you need to do for, I don't know, 1, 2, 3, 4 nodes, maybe 5 is not that much. But once the kind of distance, the amount of work you need to do more when you're going from 5 to 10 or 10 to 20 or even just 25 to 20 to 25, start actually scaling a lot more. The complexity of what you're doing is scaling a lot faster than what you're increasing. But usually customers, like the business side of things, doesn't care about that, right? They want to scale. So if we want to find a generic solution to this, what is it? And that is then operators. And again, Anton gave a really nice presentation on how to use it in practice. Here is a little bit more kind of context. So Kubernetes is an open source container orchestration system. Its kind of purpose is to solve operational challenges with regards to scheduling applications. Or kind of orchestrating. If you have an orchestra, then kind of how do you make all the instruments play well together, right? That's a point of Kubernetes, solving the kind of complexities which regards to this. It is already almost 10 years old. It was created in 2014. It has more than 80,000 contributors, so it's essentially the world's, I don't know, third largest open source project or so, depending on how you count a little. It runs in all environments, from your own data center to the cloud. My first contribution now 9 years ago was to port it to Raspberry Pi, so it also works on those small ones. Highly recommend that. But then why people find it complicated is that it's super extensible. Like, we can't get this kind of unopinionated thing where it runs from your own data center to Raspberry Pi to big scale cloud. It needs to have a lot of parameters to configure it, and that's why we can't just say that this is the one size fits all solution. So that you can configure literally everything, which makes it. And what I will show here is the principles are quite simple. The implementation of some of these principles and kind of just the amount of configuration you need is sometimes less trivial, but still once you understand the way of thinking, then that kind of mindset follows when reading the configuration and documentation. So Google or Kubernetes is based out of two other Google systems, Borg and Omega. There's also these papers available. You find them if you Google them. Essentially, in these systems, they learned how to deal with distributed data, distributed configuration at massive scale. And then with Kubernetes, I wanted to kind of, make a new system from scratch, taking those lessons learned into use, but also making it open source so that it's really not Google's project anymore. With 80,000 contributors, there's lots of other people that have put added their input and their lessons learned from all of the other big companies, and also small hobbyists having their inputs. So what is the architecture like? Well, we have a single source of truth, so this is what I talked about. This is the database that is replicated. For example, in tree mode, so you can lose one replica then. Or you can lose one replica and be fully functional, still serve the cluster and everything. And of course you can lose then 2 replicas while still having all the data. But then you can't serve any request because you fell under. You need to always have more than 50% alive in order to serve data. So all the state lies in this database, and it's just key value. So there's nothing, no kind of SQL, no magic with that. Then there is a REST API, which sits in front of the database, serving these APIs and making sure that validation, all kinds of policies, versioning, all of these kind of things are done correctly. Authorization, authentication, all of that kind of stuff. And everyone goes through this API server. Every single client, nobody goes to etcd directly. Then we have a lot of controllers that are stateless. They don't, so etcd is the only place that has stateless controllers, which look to see things like user specifies some end goal. Is the end goal that the user specified, are we there at the moment? So like you have this state that the user specified, we should go here. But no, actually we are here. Well, we need to start moving in this direction, step by step, going to that desired state. So that's what they're doing. There's like 28 controllers, I think, simultaneously all the time. If they don't have anything to do, they just sleep. And then, once they get something, user deploys something, then they start working. So most of the time it's just idle. But here is, so to say, the business logic of, like the policies and all of that kind of stuff. So for example, and then the node, when the node sees that it has a workload scheduled to it, it starts running it and kind of instructs the container runtime, the volume plugins, the network and stuff to set the container up. But Kubernetes can be used for so much more than just containers. It's really like it's much more generic control plane framework that you can, containers, scratch that, and then you can build something else that schedules something else, that controls something else. You don't even need the containers at all. You could, if you want to control your coffee machine, then you can control that. You put single source of truth. You say that coffee should, I don't know, dispatch at 12:05 every day, and then this controller checks that, is it 12:05? No. Is it 12:05? No. Okay, now it's 12:05. Okay, dispatch coffee, and then then you have control the coffee machine. Or that's a dummy example, but kind of it really can be. The containers, they are not the end game. They're not the kind of, you can do a lot more. But if we take the containers as an example, or any workload, then say that you had 3 nodes, but then this one node went down, power outage or something. Then these controllers will see that although before it was all okay, now it's not anymore, because all of the workloads that were running here, they are now gone. So now I need to reschedule. So now we were at the desired state, actual state were the same, but now the actual state drifted somewhere else because the node went down. So now we need to start working our way there again. So that's what kind of sets Kubernetes apart to most other systems, that it actually lets you define the end state, not just tell Kubernetes what to do now, but say that at which state should you always be, no matter what other stuff that happens. So it's really a control plane for any infrastructure. So it has automated controllers with operational knowledge, such as I know how to schedule workloads nodes, or I know how to heal applications that are on failed nodes, or I know how to configure service discovery or something like that. So, and then we want to control maybe the coffee machine, maybe I don't know, in control theory, usually we have these kind of pipes and tubes and tanks and whatever. But then now in this case it's Docker, maybe some workload, maybe some network, maybe some storage, maybe something else. But we want to control some target system because we don't want to wake up at night when shit hits the fan and things go haywire. So this kind of mindset is called control through choreography, where we have kind of these small Unix, like small pieces that do only one thing and one thing well. They know exactly how to operate some small part of the system, but then they, in orchestra, they kind of together keep the whole system in balance. So all the user intent is stored in the API server, but then the business logic is split into these controllers, actually manipulating that system that we want to keep in control. Why do this? Because chaos is inevitable. Anyone that has, at least my desk looks like this, maybe someone's file system looks like this, maybe someone's kitchen looks like this. Like it actually it's actually one of the laws of the universe that entropy or chaos increases over time. Some even say that is what defines time. And the Google finding, this is from the Borg paper, failure is the norm. That is something we need to take into account before it happens, not after the fact. So we need, when designing our systems, we need to assume that there will be such great amount of failure that we need to build code to actually fight against it. Not that like just, okay, push it now and hope that nothing bad happens, Those are two different mindsets. And this is really a model built for failure. So that we assume that our hardware is going to fail, we assume that our network is going to fail, we assume that our storage is going to fail, and all of the other things as well. That's why we do it this way. Again, yes, it's a little bit more complicated than if we just assume that failures would never happen, but this is real life. So entropy systems become less ordered over time. We start with a perfect orderly state, and then you have run say this is an on-prem system. We get from the manufacturer the servers. Everything is in order. 1 week later, half of the servers have burned down. It's dust everywhere, and nobody knows what software is where. That is the way of life, right? But and this is literally the whole there. Also in engines and stuff, there is no way to make a perfect engine that wouldn't increase this entropy. So how could we assume that there is a way to make a program that doesn't, create temporary files and mess up the registry and, create garbage in all places, clog the RAM, all these kind of things. So the kind of one fun analogy that I'm using is my dishes are clean before I eat lunch. Now entropy has gone up. It's all messy in my kitchen, so I need to do the natural thing, reverse the process. I need to create order again. Of course, order is something I define. It's very subjective to everyone, how they want to have their order in their kitchen. But I need to expend energy. I need to expend time into this reversing process. But if I don't do it, then I won't have any clean dishes. So, you have the shiny new server. You have it a week in production. It looks like this, and then and this is metaphorical, it's software just as well. So we need something to reverse this in this process, and that is Kubernetes. So it's a dishwasher of servers. So now we need to define what is order, what is chaos. So we have 2 states on a map. Those are declarative. Those specify the what, we are here. But now, an action, when you click a button in a UI, that is an action. Often when we think about control, computers don't know, when we say, start virtual machine, the computer doesn't understand that we want to have the machine always on. Right? If it shuts off for some reason, then the computer, unless we have told it that it should always be on, then it won't restart the machine necessarily. So that's the difference between an action. This is an action movement from one place to another, whereas the state is something we can tell a computer and we can kind of codify and the computer can understand. So main point being, you need to define the state that you want to be in, otherwise there's no program, there's no way to take you there. No one knows. So the key takeaway is that any system becomes less ordered, more entropic, so you need some periodic corrective action. Periodic because if you do it too seldom, then it will stay in such chaos that it's not manageable anymore. So for example, take the .NET upgrades. Now it's still possible, was it 10 years?
Yeah.
But if it would have been 100 years,
yeah,
maybe we couldn't restore it anymore because we have some other completely new file system or whatever. We don't code using bits anymore, but qubits. I don't know. So we need to kind of periodically do these kind of corrective actions, keep with the arrow of time towards the declarative desired state. So that is the operator. So an operator, much like a human, this is a software operator that actually encodes the human knowledge that we have about how to operate the system. So, for example, this lets us delegate, well, according to the kind of official definition, repetitive human activities that are devoid of lasting value. So, essentially waking up 2 a.m. at night just to click, it's two more replicas, that doesn't have any lasting value. Then, 2 hours later, the boss is angry with you if you haven't downscaled those replicas again because now you don't need them anymore, and they cost a shit ton. So with a software operator, then we can actually codify these kind of things. So we can keep the infrastructure in control, continuously minimizing the drift between the desired and actual state. We get resource scalability because now we can actually scale to much bigger extents than before. But we also get the monitoring scalability where we don't need to have humans looking at the dashboards. We can actually have the operators, the kind of software agents, looking at these dashboards, looking at derivatives, correlating different types of data, and then putting it all together and, you know, blasting the big notification when something actually is wrong. But then with that, we can also tune configuration parameters automatically, for example. And then knowledge scalability. Now if we present, so what Anton showed was that it's possible now to run a Postgres database in production using just a simple UI, where you don't need to know everything about how to use PG Postgres tools to do upgrades and to do backups and all of these kind of things. You just use this kind of more high-level API where you tell the operator what to do and then it does it. So if you wanted to learn then how did the operator do it, you can actually go and look at the code. You don't need to ask that, you know, coworker that left 10 years ago. You know, then you don't know that anymore. That knowledge is lost. But if it's codified, it's still there. So yeah, we can avoid the sysadmin overload. So instead of humans operating machines directly, we have now an industrial revolution where actually we are operating, you know, another layer of indirection. We are operating automation that is operating machines. You know, all of this kind of borrows a lot from control theory. It is really control theory, which is, you know, what is keeping our planes in the air and like everything running in the analog world, right? But this is control theory for the software world. So here is an example of a TIDB is a MySQL compliant database, essentially, that emulates a Spanner, Google Spanner that I talked about. There's two projects that emulate Spanner model, essentially, that are open source or ish. Two main ones, TIDB and CockroachDB. TIDB has one of the kind of, say, purest similarities with the Spanner design as it was lined out in the Google paper. TIDB is open source and it consists of two parts. I don't know if I had it here, no. Two parts, one part that translates your the SQL interface to key value, and then that sends the requests to a separate key value store. And the key value store is a graduated CNCF project called TIKV. So TIKV can be used completely standalone of the SQL layer, but if you want to have SQL, then sure, just add it. So it kind of does all of these features, right? Dynamic monitoring, backup, restore, up downgrades, all of these kind of stuff that Anton showed. So essentially, we now have a target system. We want to kind of keep this in control. Now the target system is our database. The operator acts on the target system when needed, backups, you know, all of these kind of things. Tells you that, okay, it was successful or not, and then just keep on looping. So what I did in this demo, when I had it, was that I configured 3 cloud VMs for the kind of SQL layer, 3 cloud VMs for some metadata store, and 3 cloud VMs for the key value store. And then I installed the TIDB operator to do this using GitOps, the GitOps engine Flux, also another graduated CNCF project. You see the theme here. Then Prometheus I installed as a monitoring stack. Prometheus is also a graduated CNCF project. Grafana for the dashboards. And then I created one of these kind of, to Kubernetes you can, so what is the interface for this operator? It's actually, you can extend the Kubernetes API server with your own data models called custom resource definitions or custom resources. So this TIDB operator, when it starts up, essentially it registers one of these APIs that you can use. So you can now just put to the Kubernetes API server the definition of how you want your TIDB cluster to look like. And then I did some advanced config, and this I did this demo on UpCloud, a Finnish cloud provider, because I thought it was cool when I was presenting in San Francisco that, to have a Finnish cloud provider. So with this demo, I upgraded from version 7.1.0 to 7.1.1 using GitHub pull requests because I could. And then the operator, I didn't need to start upgrading this database manually. This operator just upgraded the cluster for me while maintaining a 60,000 requests per second without any reconnects, while monitoring and all of that. So essentially, I had my front end is GitHub, so I had my declarative configuration, my end goal of where I wanted things to be, as JSON checked into a GitHub repo essentially, and then Flux, the GitHub engine, takes that desired state from the GitHub repo. It's all kind of configuration. It's not necessarily code. It's just like static JSON. Puts it into Kubernetes, and then at this point, Kubernetes is a kind of it's an extension to Kubernetes. So Kubernetes native controllers don't know anything about what to do with this. But the TIDB operator knows. It sees that, okay, the version has changed, so I need to start doing a rolling upgrade, right? So when it starts doing a rolling upgrade, then it creates new Kubernetes resources, it removes old ones, etc. So those are the ones that the Kubernetes normal controllers act on. And then eventually the node executes these new things. So we get kind of this, so the good thing with the TIDB operator, it didn't have to solve all of the scheduling problems, all of the kind of other hard problems about it. Can kind of piggyback on all of the things that Kubernetes already provides as a platform to do all of these things. So the TIDB operator or any operator doesn't have different modes for AWS and Amazon and AWS and Azure and Google and Raspberry Pi. It's all the same code. So what I did, I had the configuration here, TIDB cluster version is declarative. I bumped that to 7.1.1 from 7.1.0, and then I waited. It took maybe 15 minutes or something like that. And here are the graphs. So you can see that it eventually, first it does the draining of the, it spins up a new thing, it does the draining of the old thing so that the leadership of the raft groups are transferred. Then you see the downward curve here. CPU usage goes down to 0 because it's killed. A new one starts up, and then of course some of the other TIDB kind of when there are only two for momentarily, they have a little bit of higher load. Same thing there on I/O. Same thing here. You see that they drop one by one, but they come back up like, of course, before. They don't kill all at once. They kill one, have one more up, and when it's healthy, cluster can recover then continue. Queries per second here is like around 60,000 requests per second. No failed queries. Yeah, essentially that. Now this one there were only select queries, but I tried it with both write and select, and it worked just as fine. Of course, we didn't get as much requests per second because you can't if you both write and read, but still. So for this, I didn't have to do any manual service discovery, no TLS setup, scaling, version upgrades, reconfiguration, all of this kind of stuff. The operator handles that for me. So yeah, this is one example then of how not to operate the machine directly, but how to utilize automations that then operate the machine. So which Kubernetes it is, but Kubernetes is a platform for platforms, on top of which you can build more platforms, right? So So that's that. If this interests you, you can check out my thesis, in which I detailed all of this kind of in a much longer format, but still it's kind of for educational use. My GitHub name is Luxas, Lucas with an X, and research. And here is kind of more academic format of why these things actually work. I also highly recommend reading the Mark, and also referencing Mark Burgess, was a professor at Oslo University. Did a lot of similar research, but 30 years ago already. Then also the Kubernetes podcast, you can keep an eye out for that, because we will have soon podcast about that. There's some other good talks about control theory and kind of how those relate to Kubernetes. It's all the same things. Yeah, that's that. Thank you.
Where can I find the links to the talks on the control theory?
I can send them to Meetup group.
This example, I guess the operator and database that you were upgrading the version of.
Yes.
Is there kind of a use case or setup that only the operator would run on the cluster and it operates something external? And
Yes. Yes, definitely. Like that's the more common use case actually. I would say that it operates something externally. So like there's operators for DNS domains, for example. So then, when you have something running in your cluster, or you have some kind of claim for I need to have a DNS mapping somehow, then it actually goes ahead and creates that in the DNS provider or storage plugins or anything else you kind of would like. So operators are literally meant for this kind of way of you now have a baseline. You can execute stuff in the cluster if you want to kind of create extensions or other arbitrary things, but you can also control really anything like the coffee machine. It's not like now you have what Kubernetes provides is a control plane framework essentially. So you have the database in which you can store your state, right? etcd. It's extensible, so you can create your own API types, your own kind of data. I mean, clearly, if I have a coffee machine, I need to store somewhere the policy for how I should manage the coffee machine, and I also need to check, when did I last, clean it, right? So I know where to start the cleaning routine of the coffee machine. All of those are custom data that certainly are not shipped with the official Kubernetes product, nor should it be. But I can I can extend that with myself. But the fact that Kubernetes provides this for me, just as kind of a database essentially, it's kind of and it provides a lot of other good things like watching and there's this huge library, really well created controller library, which also kind of lets you take inputs from lots of different sources and kind of react to different changes and still kind of have this reconciliation. So like a framework for how to do that. There's the main one is called Kube Builder or controller runtime, but there's also other frameworks in the CNCF that kind of make this possible and have focus on different things. So there's an Ansible operator and there's a Helm operators, and there are like all kinds of more specialized things, but the generic frameworks can be used for really anything.
Is there some nice scalers monkey, like if you want to test the resilience of the platform? Like is there something, I know litmus scalers is one thing.
Yeah, I haven't tried it, but I would say that one is probably the most.
Like I know litmus scalers is good if you want to test in-cluster stuff, but then if you have like a coffee machine, it probably doesn't know how coffee machine works.
I don't know, like I would assume that litmus scalers or some of the other chaos engineering projects would have some library to kind of that can be reused. be surprised me if not. But yeah, of course, there's no coffee machine chaos monkey yet.
I never had a personal use case for Kubernetes yet, so I have no image of were they controllers or operators, the modules that keep track of, or like, what, could you give me an example of, you said there were 45 of them in Kubernetes?
Yes, like 30 I think, yeah.
30, okay, sorry. So, could you give me an example of what they might do, and why are there that number of them,
yes.
and why not more?
Yes, so I don't know how many here have created a deployment or know what a deployment is in Kubernetes? Okay, a couple. Okay, then I will tell about it. So essentially, Kubernetes provides a couple of different levels of abstraction. So the lowest level of abstraction is that I have one application instance. And that is essentially one or many containers that are running on one host, one physical kind of node. That of course means that if I put this application instance on this node, and this node goes down, somewhere, then I don't have this application instance anymore. It went to trash. I was running something there, I was doing some useful work, but power outage got me, and now I can't do anything. So if this was the only thing that Kubernetes provided, this application instance thing called a pod, then don't have power outages, right? Or like, cloud provider failures. Yeah. So we need some kind of, higher level thing. So the thing, so that's one controller. So, there's one controller on the node. So on each node, there's one controller that looks, watches the API server and asks that, do I have any pods to run? Do I have any applications instances to run? Once that is in the database, then it kind of downloads that specification, that desired state, actually puts it on the node, like literally as a cache, because we can lose, at any point in time, we can lose connectivity to the control plane, right? I don't know I hope people aren't afraid of flying, but that is something that real planes also can do. For example, turn off their engines and start again and kind of do all kinds of stuff. So that's why one of the things that they were kind of inspired by. So the designs of systems are that, okay, you schedule all the things, you have all the workloads running, but then boom, your control plane, where all of the data is, would disappear. What would happen? Everything should continue working, because the data plane and the control plane are completely different. So if you have all of the kind of workloads running in your cluster, then they can still communicate there, no problems. Like everything still works, although nobody can get any updates. But of course, if you then lose some nodes to power outage and stuff, of course, then it can't self-heal anymore. But at least the data plane is kind of, nothing happens if you lose that. So that's why they kind of keep the cache on the nodes. So that's one controller, the node agent. Or in that node agent, there's probably 30 controllers in that one as well, for networking, storage, device plugins, GPUs, all of these kind of things that happens on a node. But simply said, there's like, we get the specification for what we should run, we run it, right? No matter what happens, until we get further instructions. But then what to do about this, the other thing, we don't have any replication. If we then wanted to run 3 application instances, we would want to have a web service that we want to have 3 replicas of. Then we would need to specify 3 different objects to the API server. That is a little bit cumbersome, because I just want to have one object to which I specify how many I want. I want 10,000, okay? I don't want to have to create 10,000 objects and keep track of how many they are as they go up and down. I just want to say that here's my one object is as a template for how my application should look, and now I will have a controller that just always creates 10,000 of these, if that's what I put. So That's so the application instance. Then we have the kind of application, I don't know, template or set. It's called replica set, pod replica set. The replica set then creates as many pods, just one controller that reads the replica set definition and creates as many pods as needed. It doesn't know where to schedule them, it doesn't know anything. It literally just copies the JSON thing, puts it into another and submits it to the API server. But once it sees that some node has gone down and the pod with it, it now creates a new pod. Because now the desired state is not the actual state. Right? So that's the second layer. But now what happened? But this is still immutable. So like we can't, if we once created the template of what to do, we wouldn't be able to kind of, for example, bump the version from one thing to another, because then we would need to kind of scratch all of the like we would need to delete all of the 10,000 at once and recreate all of the 10,000 at once. So what we then have is a third layer, which is then in its normal mode, it's called a deployment. In its normal mode of operation, when it's first created, it just creates one replica set with the exact same JSON as itself. But this deployment is mutable, so you can change anything in the template, as you like later. So if you change the version of your containers or something like that, it will now have, so the replica set has created 10 pods of version 1. And the deployment has created one replica set. But now when you edit the deployment to say, I want my container to have version 2, then it will create another replica set on the side. So now we have two replica sets. One which has 10 and one which has 0 pods. And then it will have, say the replica set, create one pod. Okay, so replica set controller creates one pod. Now it says to the other replica set, the old one, that you had, I said to you that you should have 10, but now actually just have 9. So it's just one write to this replica set object. Then the replica set controller actually goes and deletes one pod. And so it goes on. So the deployment controller sees, okay, now I'm successfully running only 9 old ones and 1 new one. Then okay, I bump the version of the new one. Now we have 2 of V2. I can remove one more, and etc. So it goes on. So this is a way of and of course, if it starts failing, or if the metrics, goes to shit, or something like that, a bad rollout, then we can roll back. Then it never proceeds with this operation. So we can kind of have these kind of a lot of business logic, but each controller is super simple in the sense of the replica set controller only looks at one replica set, copies the JSON and creates multiple of those. The JSON, the deployment controller only does this, bump one, remove one, bump one, remove one when it's changed. And the node only, downloads the individual instance template and runs that, right? And so on. So that's why there are so many, because they do one thing and one thing really well. And that's why you have these layers of, and if I create a deployment or if I create a replica set, I don't need to know what's happening underneath. I can just rely on that API surface that it gives me. So, which also means that you could use a deployment controller even though you had some completely other implementation of, maybe you don't have containers at all. Maybe you have something like WASM things, or maybe you're actually running VMs. You can run VMs technically, instead of the containers, or do whatever crazy thing you might like, as long as they fulfill the kind of basic guarantees of isolation, for example, then it's good and networking. So that's a kind of way to kind of layer the system. So now you can actually start, and then, for example, what happens then between the replica set has created a pod, it's by default unscheduled, so it's not part of a node. But the scheduler is another reconciler, whose only job is to look at, are there pods that are not belonging to any node, and are there nodes that have any free capacity? Okay, there are free capacity somewhere. Okay, I will pick one, I will match this pod and this node. And that's its own kind of controller, its own problem space. So then that's the kind of control of choreography, control through choreography that we have. Then these 30 controllers together sing in harmony and actually make a system dynamic and kind of well-functioning in any environment. Because then when you need to extend, you only need to extend small parts of it. But for example, if you are on-prem, on your own data center or something, if you're on my Raspberry Pi, maybe I need to extend something with regard to networking, for example, or maybe give storage in some specific way or something like that, because I have my disks here. Then of course you need to that's what you need to configure and tell Kubernetes how to use, and those are actually external to Kubernetes. Networking is not part of Kubernetes, storage is neither. They are kind of coming out from the outside through well-defined interfaces. In fact, Kubernetes doesn't know how to run containers. It just pipes it to a daemon and says that run a container. And if nothing is answering, I mean, even like Docker could be one, right? But there's many other implementations of this container runtime on the other side. And if there's nothing listening there, nothing happens. So Kubernetes is like, at its core, very kind of, it's a set of controllers just, piping data from one place to another in the way that you wanted, in the way that you specified that the end goal should be. So that even stuff breaks and, failed rollouts and failed nodes and all of this kind of stuff, then it kind of continually heals towards a state that is best known to be stable. So that's the kind of philosophy of the thing.
Yeah, that actually answered the question really well. Yeah, thank you.
Short answer.
Yes. It's a whole own presentation on how that works. And of course I cut corners. Yes. Any other questions, or do we go to networking?
Maybe we can do this question as networking, but the coffee machine example that you gave here, do you have come up with any good ideas where to misuse this technology, in a way, or do you know something?
Yeah, I mean, there are people that, for example, order pizza with it.
Okay. Okay, like a desired state.
Yes.
Okay.
You send a desired state of, somewhere of like, this is how many pizzas I want, and from these delivery places, and then the controller goes and
figures out
where you are, and you can make it as complicated as you like.
Yeah, because it seems to be so over generic, so there must be like
one cool thing I heard about, I was at the security meetup in Helsinki, and there was this dude who he has like a small pen testing firm, and you have to do some scanning, some basic reconnaissance, and he had this in-house operator where he pretty much tells Kubernetes that now I want to scan this stuff. Kubernetes schedules jobs, so instead of just having one node doing like a 24-hour scan, just small pieces. You scan these 3 ports on this IP, that type of thing. And then instead of having a VM or something somewhere that has all the scans, it just schedules nodes in Amazon US. So you have like this huge ass IP range. And you get parallelization, and then the customer can't really see where the scans are coming from. So the customer never knows getting scanned. Because there is like always a new IP, just a random request.
Yeah, and it spans over time so much.
Yeah, and like insane parallelization, because they can use like any cloud, pretty much. That's a pretty cool thing I've seen in a while, or like heard about.
one other cool thing that when you set jobs, so again, job is another kind of primitive built on top of pod directly. So it's not like it's deployments, replica set and pod, but then job is kind of directly creating, the job control is creating pods directly. And those are for short-lived things, so like batch stuff. So the pod, runs the thing once. When it's done, okay, kill the pod, and just say in the status of the job that I'm done. I executed fully. Perfect. And then of course on top of job you can have cron job, right? Which creates jobs on demand. So you see the thing. But what they did, one of the coolest demos I've seen at KubeCon was when CERN they made this Jupyter notebook, and with their template for how to find the Higgs boson, right? And their kind of graphs and stuff. And then they took the data, like Anton Gano said in the previous example. I don't remember how many peta or exabytes or whatever it was. And they did preload it to a cloud before, and they were sponsored by this one cloud to do it, because if just piping in the data would have cost millions. Of course, the ingress and egress traffic cost. But they were sponsored for this demo, but still. They had put the data in a cloud, like in some buckets, but then they with this one thing then spun up 10,000 jobs, or was it 100,000 jobs? I don't remember, maybe 10. And this was a keynote at KubeCon in Barcelona. So a keynote is 20 minutes. So, the first 7 minutes, 10 minutes goes to say, hi, I'm, whatever, working at CERN, I'm an infrastructure engineer, these kind of things. And then, telling about the Higgs boson, telling about CERN, so then in that demo, then they click enter, okay, schedule all the 10,000 jobs. And these jobs then massively parallel, like how many, probably 5,000 nodes or something like that, working in parallel. And then it took a small part of the data, processed it, and it uploaded. So during the time of the keynotes, so like probably execution time was under 10 minutes, they had rumbled through all of the data required for rediscovering the Higgs boson, and they got the live data feed into the Jupyter notebook, and there it was exactly as it started from blank, but then you could see. Of course, no, I couldn't see, but they told that they had marked the point. This is where to look. Like, this is the thing that should be like this if the Higgs boson exists, right? So then they did that. That was an extremely amazing demo.
So who validated the data which is processed by the node before uploading to the database?
Say that again.
The data which is uploading to the database.
Yes.
Who validate the data?
So in this specific example, or in Kubernetes in general?
In general.
In general, like the API server enforces that like you can only send valid data. So that's why you always go through the API server instead of being able to write directly.
So each and every data will be verified before sending to the database.
Yeah, all of the configuration will be validated strictly before sending anything to the database. Yeah. And according to all the versions and stuff. But yeah, before this Higgs boson example, they when they had processed the data, they just sent it directly to the Jupyter live demo environment. But yeah, that was an extremely cool one. It is on YouTube, so you can watch it. Ricardo Roja and another guy, 2019 in Barcelona. It was called something, rediscovering the Higgs boson.
Using public cloud. That was the same part, because CERN has like amazing data set.
Yes.
But
Yeah, exactly. That was it was a public cloud. Yes.
Yeah.
Yes.
That's great. Yeah, just the validating part. That's so nice with Kubernetes, because like as a cluster admin, you can give people quite like free access, and then you just put in your own validations. Like you can do this in Kubernetes, but in our clusters we don't allow this. And then if Dave, the developer, wants to do stuff, he can write the YAML, but then as soon as he wants wants to push the YAML to the cluster will be like, no, you have to fix these and these things.
Yeah, like it is. If we wrong data goes to the database, so that we have to do the process again.
Yeah, so you
It cannot be like you say it as reverse. You have to create the part and do the part again.
I mean, you can just revert to, so one of the nice things I showed in my example there, like the GitOps thing. So then, like, the idea is that you store the configuration as you want it over time in Git. So you're a team, you collaborate, you have different kind of Git repositories and Git different files in that repository and folders and stuff. So then everyone is kind of aware of what is actually the thing that we want to deploy to production by putting in those configuration there. And then the nice thing, side effect of, you see also how all of the infrastructure has changed over time. So you can see that, okay, on this date, we deployed this change, we updated our production web servers from Nginx 1.3 to 4. That was the person that did this line of code. Okay, we rolled it out, oh, fuck it, everything broke. Okay, Git revert. And then we know that then kind of, so I said, like, for example, the deployment controller or other similar controllers, they can kind of intelligently see that if through metrics and stuff, if the deployment goes bad, but eventually you want to fix your configuration, and then you can just do a Git revert because you have all of the kind of intermediate states as well. So that's one of the nice things with that. But yeah, of course, it's best to not get invalid data anywhere in the first place. And that's why policies that preventing you from doing so is a good thing.
One thing that we don't do yet, but I would like to have implemented at some point, is also so you could have a production environment in your own Kubernetes cluster, or in your own Kubernetes cluster in the cloud. So like a developer could actually work in exactly the same environment as the production workloads run. We aren't there yet, but like at some point we'll try to be there. Because like now if you're just some front-end developer working on your local machine and you have your own proxy and your own whatever setup to get your work done, there's still so many different things that don't match with the production cluster that it's hard to tell, like, is this thing actually working? It works on my machine, but will it work in the cloud?
Yeah. Regarding this generally, there's a saying of every difference between dev staging and production will eventually lead to an outage. This is not Kubernetes specific, this is like with anything. So yeah, it's a classic.
Isn't that what like Minikube?
There are lots of options nowadays. I just have to pick one and start poking around. We should do one of them live exercise thingies again now.
Yeah, we could do. I have all the code is in GitHub, so for doing that. And it's a fun exercise in using Kubernetes as well, because of course, so the demo environment, yeah, actually we just need to find someone who pays for the cloud bill. Maybe I can ask someone.
I'll go for sure.
Yeah, probably. Yeah, it's
Has Vale moved already?
Not yet.
Not yet. So we still have
in 1 month.
In 1 month, we still have 4 weeks then.
Just if you reboot this one. This is a controller going. So here is a presentation from 2020. so the demo environment itself, like for learning Kubernetes, is of course running in Kubernetes. So this time I was doing it in DigitalOcean. So the idea is that if you're learning Kubernetes, you shouldn't have to install all of the stuff on your local machine, because every time we've done it, someone has some enterprise settings on the laptop and can't install anything, and someone has a corporate firewall and the third has, it never works. And then the Wi-Fi, I'm pulling gigabytes of images, it breaks. So that's why we do it in the cloud. This is a good example of kind of how to put stuff together. So we're actually running Visual Studio Code is written in JavaScript or TypeScript or whatever. So it actually runs in the browser as well, really fine. So you can just serve it or an HTTP port or a web server. So then what we did is we created one cluster per attendee, and so like 50 clusters or 30 clusters or something like that. So everyone has really their own. Like we could do it more bin packing, of course, but this is like for learning. So then we give you complete admin access to everything, and if you break it, you break it, right? And there's a load balancer. So internet, you are here, you go to cluster 1, 2, 3 or something like that, .kubernetesfinland.com. It routes to the load balancer. The load balancer decides based on the domain, that is it the top level domain, then it goes to code server. Is it for the load balancer, then it goes to the load balancer UI. If it's for some application, then it goes to routes to the application, and then you can make whatever you want more. And how do these, and what we talked about the controllers that do something else than Kubernetes. Like now we define in Kubernetes these kind of services that we want to have domains registered for. So that's why we have a controller that actually goes ahead and creates these domain records in real time. Of course, DNS propagation is always, I don't know, 15 minutes or something like that. But anyways, create the record so I don't have to do it myself. And the even more cool thing is we want, of course, to have all the secure HTTPS communication of this. So it can be the load balancer traffic, or it can be something else as well, like cert manager. Then the cert manager actually also has access to the domain service and can do the DNS01 challenge for Let's Encrypt to acquire a HTTPS certificate for these domains as well, completely in an automated manner. So yeah, then for learning Kubernetes, the only thing you need is web browser, go into a URL and boom, you have your own cluster. Can do whatever for some pre-installed binaries and stuff. And yeah, then you can do whatever, and you actually have real internet. You can open literally anything to the internet then. So that's a cool one. Yeah, I was actually thinking about it, but we should see if someone has some cloud credits for us.
Friday night at this
I'm presenting on Friday night. After that. Yeah. But yeah, there was on the side. Yeah. Would there be interest?
Yes.
Hands-on, so we can do it. Okay, perfect.
Yeah,
For sure.
Yeah.
Good. Yeah. But that's yeah, that was a way too long thing, but but
Yeah.
good that there are lots of questions. Yeah. Yeah, let's I guess end the official part here, and then we continue with networking until how long can we
I
stay
think
here?
until 8 o'clock.
Okay, so
Yes.
10 minutes.
So we have like 10 minutes or maybe
That's good.